Okay, this is just going to be a quick video. Not really any new information here, just different ways of writing things, where I'm going to talk about different ways that we can represent the energy change that occurs in a chemical reaction. Keep in mind that when we're doing this, we're always going to be talking about energy changes that occur with the particles. And so this is from the perspective of the particles, not the surroundings. So the first way that we can represent the energy change in a chemical reaction is with a thermochemical equation. This is where we could take a reaction like the production of water and we could represent how much energy is released in that reaction by writing out the chemical reaction with an actual energy term sitting on the side of that reaction. So in this case, we're producing, let's assume it's gaseous water, or water vapor. And when that happens, it would be an exothermic reaction where 241.8 kilojoules of energy would be released to the environment. Now we see here, this usually would be written as kilojoules per mole. But I've set up this equation so that I have 1 mole of water being produced. So if I know I have 1 mole of water, then I know I have just the 241 kilojoules because I'm dealing with just 1 mole. I could write this as a proper balanced chemical equation with no half coefficients. But if I did that, and I was looking at the amount of water vapor that's being produced, of course I would have to have 483.6 kilojoules, because if this is how much I have per mole, and then I have 2 moles, then I would have that amount of energy produced in that reaction. So in a thermochemical equation, we just have to get the amount of energy right in ratio to the coefficients of the other particles in the reaction. I can also write this as a molar enthalpy. So this same reaction, H2 plus 1/2 O2, goes to H2O, gas, could be written with a delta H value over here. And that delta H value is assuming the same ratios that are in the equation. And here, because of the way I've written it, it would be 241.8 kilojoules. I use a negative to represent the fact that my reactants are going to a lower state of chemical potential energy. So they've decreased, or they've been negative. And this again would represent an exothermic reaction, or energy available to the environment. So that's how you use a molar enthalpy. Again, the same rule applies here. If I had the general equation written as a proper balanced chemical equation with proper coefficients, no half coefficients, then of course my delta H value here would have to be twice as much, or negative 483.6 kilojoules. So I can put it right in the equation like this, or I can put it sitting off the side on this. Before I go further with this, it occurs to me I should show you a thermochemical equation for something that absorbs energy. So let's say, for example, that I'm going to deal with sodium chloride, solid, dissolving to its ions in solution. This would be an endothermic reaction. Now I don't have the actual value for this, so I'm just going to make this up. And because this is endothermic, or energy has to go in, I don't show the energy coming out at the end, I show it going in. So let's just say that this would cost 20 kilojoules per mole. And so I could write it like that. Changing these for the same reaction, NaCl, oops, not plus, goes to Na plus and Cl minus, both of those, they're aqueous in solution. I could write this as a delta H value after the reaction, and this time, because it's endothermic, we assume that these products are going to these reactants are going to a higher state of chemical potential energy. So we get positive 20 kilojoules. So there's a thermochemical equation that's exothermic and a molar enthalpy stated as exothermic. And here's a thermochemical equation that's endothermic, the energy is going in, and here it is stated as a molar enthalpy. These molar enthalpies can get special names depending on the type of reaction that's happening. So we could, for example, have a molar enthalpy of combustion, and that would be associated with combustion for whatever species we're dealing with. So let's say we had something like methane burning in air to form CO2 and H2O. Instead of just putting my delta H off the back, I could be a little more specific and say that's the delta H of combustion. That really isn't any different from saying molar enthalpy, but when they say enthalpy of reaction, they're typically going to have some specific type of reaction that you're looking at. Let's say the delta H of neutralization of an acid and base or something like that. In the end, we still put the delta H's off the end, they just get little subscripts, and so it's not really any different from representing it with a molar enthalpy. Finally, potential energy diagrams. And I've been doing a lot of these as we go through. I just haven't called them this properly. So if we imagine that this is the chemical potential energy of the reaction H2 plus 1/2 O2 goes to H2O, then I can represent this change in chemical potential energy by looking at the actual values of potential energy of the particles before and after the reaction. Before the reaction, because I'm dealing with all elements, my potential energy would be 0. After the reaction, because I'm dealing with an exothermic reaction, I would drop to negative 241.8? Yeah, 241.8 kilojoules. This diagram, as it's shown, is assumed to be per mole. And so we can see our negative delta H in this graph. So that's how I could use a potential energy diagram to show the release of energy associated with an exothermic reaction. While I'm here, I'd like to take this second to talk about how this relates to the diagram for the surroundings point of view. So if this is exothermic releasing energy to the environment, and I track the temperature of the surroundings over time, what I'm going to see is that as this decreases, this temperature is going to increase. So this is what it looks like. This is our positive change in temperature associated with this exothermic reaction. Notice also that I've left a gap, a little gap in between what's happening before with the reactants and what's happening with the products. I'm going to talk about what happens in that little gap in the next unit, but right now we're not paying attention to what's happening during the reaction. We're simply comparing before the reaction to after the reaction. Finally, a chemical potential diagram for an endothermic reaction. Here, we might say that NaCl, sitting as a solid, sits somewhere down here at some value. I'm just going to make this up, like negative 350 kilojoules. And in our endothermic reaction, it's going to come up here to some value, negative 330, that is above, but still not up to the 0 level. This is, of course, our chemical potential energy. Here we can see our positive change at delta H of 20 kilojoules. And if I were to look at the surroundings, recognizing that that increase in potential energy has to come from somewhere, then if I looked at the temperature of the surroundings and they started high, they would reduce a little bit as they provide that energy to this reaction. And that's how an endothermic reaction would look from a chemical potential energy and from a surroundings perspective. So we can put the amount of energy directly into the equation. Just make sure it's in ratio with the other things, and then you could use mole ratios to figure out exactly how much energy is produced in your situation. If it's on the product side, we assume energy is coming out, or it's exothermic. If it's on the reactant side, we assume it's going into the reaction, so it's endothermic. We could write it off to the side as a delta H value. These delta H values are assumed to be for 1 mole of the reaction. And again, we can put this as exothermic if it's a negative value, showing that they went to a state of lower chemical potential energy, releasing energy to the environment, or as a positive value for endothermic reactions. Finally, we could give the graph, if we talk about the enthalpy of reaction, we can name these specifically based on the type of reaction, and there's all kinds of names that can be used here. And finally, if we look at exothermic in the surroundings, we can look at how the energy will actually change on a graph. See the delta H's, and then I did these diagrams. These are from the surroundings point of view to show how the temperature would change in an endo and exothermic reaction.